And what we're going to do now is basically get into what's called the kinetic molecular theory of gases. And one of the things that we do in there is we're able to figure out, based on the pressure that these individual particles of gas are exerting on the inside of the container, different properties of that gas. We start out dealing with kinetic energy. And definition of kinetic energy is it's equal to 1/2 the mass of the object times its velocity squared. For instance, for hydrogen, they have a list in here, a table, I believe, of speeds. Oh yeah. You don't have to memorize or anything. The table 13.3 gives some speeds for gases at different temperatures. Say at 20 Celsius, hydrogen. So what we're going to do is we're going to calculate the kinetic energy of these hydrogen molecules at 20 Celsius. The thing is, though, that in order to get units that we deal with, like joules, you need to get SI units, so the mass is going to have to be in kilograms, right? And distances in meters, times in seconds, and so on. So basically, what we can do is we can now plug these in, calculate the kinetic energy of a mole of hydrogen molecules at 20 Celsius. And for a mole, we'll get get about 3.6 kilojoules per mole. You guys follow that? do it per molecule. Each molecule then, we calculate, has that kinetic energy about 6 times 10 to the minus 24 kilojoules. So when it hits the inside wall of the container, that's how much energy it hits it. Well, the thing here is that this number right here, I just kind of looked it up in a table and put it in there, but it ends up that not all the particles in that gas have the same speed, same velocity. There's a distribution of speeds, and that's a real important concept. They actually have a schematic of an apparatus that they've used to measure the distribution of speeds of the particles of the gas. And it's pretty interesting. It's on page 449. And what they did is first they took an oven where they heat up the gas particles. So there's a bunch of gas particles zooming around in this oven, right? And they have a hole in it, right? And when a gas particle hits that hole, it comes out of it. And then, so basically they have a stream of gas particles, right, coming out of this oven. Then they have a series of slits. That's to collimate the beam of particles, so that it's moving in a line, a line going up and down like this. So we have a line of gas particles coming out this way. And then they have these discs that are rotating. And these discs have slits in them, right? Where that slit in the disc lines up with this line of gas particles coming out of the oven, they'll go through. And then there's another disc with a slit, right? Only it's behind the first disc, right? So you get the picture, you have this stream of gas particles coming out, that if it hits that first disc just right, it's going to go through. And then the other one, so this is turning it like this, and the second disc is turning, it's behind it, right? So if the distance that this second disc turns is equal to the distance that the gas particles travel as they go from the first disc to the second disc, then it'll go through, that stream of particles will go through the second disc. Do you guys understand that thing? And so only gas particles that are moving at the right speed will make it through that second disc. And then they have a detector over here that says, okay, did anything come through or not? Right? That's the basic setup. You guys get that? And so what you can do is you can adjust either the distance, how far behind that second disc is from the first, or its rate of rotation, either way, and do the experiment and see if you get gas particles or how many gas particles you get. The detector detects that for you. So you do this, you go through and you adjust that second disc so that you have you can tell if there's gas particles at different speeds going through, and you plot it. And when you do that, the plot looks like something like this. Depends upon what the temperature is. No. They have this graph on page 449. And you see that you have this distribution of speeds. Some of the particles, the gas particles, are moving slower, right? So it's increasing this way, right? It's increasing this way. Some of them are moving this fast. There's a lot of them in here, right? As you get faster and faster, there's fewer and fewer particles until it goes to zero, right? So there's a distribution of speeds. Now it ends up the shape of this curve depends on the temperature of the gas. If you heat it up, heat that gas up hotter. Curve is going to look something like that. What happens is, as you heat up the gas, the distribution spreads out, and the peak, the maximum fraction of gas particles that have that speed, shifts to the right. So on average, they're moving faster, right? But not only are they on average are they moving faster, but there's a greater spread in the distribution. We have more particles going fast, more particles going slow. It's spread out. Because there's this distribution of speeds, there's also this distribution of kinetic energies. Because kinetic energy is 1/2 mass times the velocity squared. Okay? And they have a plot of the fraction versus the kinetic energy, but it's basically the same idea. It's a little bit different. What this means, one of the things that this means for us then is that you can't talk about the kinetic energy of all the gas particles in there, but we can talk about maybe the mean, like the average of the mean. So instead of saying kinetic energy, we put a bar over it. The bar, it just means the mean, or the average. Okay? There's not going to, it's the same gas, so the mass is going to be the same. But what there's a distribution of is the speed. So we put a bar over the v squared. We're going to use this equation in just a minute. But first, the 5 parts to the kinetic molecular theory of gases. I pretty much mentioned these when I started the gas chapter because I wanted to build up this picture of gases in your mind. The helium particle hitting the wall and all that. What's it over there? 5 parts. Okay, the picture is this. These gas particles, so, we're imagining some container filled with a gas, like a balloon filled with helium or what have you. And what the kinetic molecular theory says is that those particles are moving in straight lines in random directions until they hit something, then they bounce off. Then when they do hit anything, there's no net loss of energy. The collisions are elastic. That's what elastic means, is that there's no energy is lost. We don't, we don't take friction or heat loss or anything like that into account. Assume that energy stays the same. The distance between these gas particles is large compared to their size. We're assuming that any interactions that might happen between the gas particles are negligible. We're neglecting them. We're going to say that they don't happen. So I think I described this last time. Two gas particles zooming around in there, straight line, random motion until they hit something. If they come close to each other, say they don't hit, but they come by each other. In real life, in reality, this atom, you can think about it as a nucleus with its positive charge and a cloud of electrons. Same thing over here. Nucleus with its positive charge and a cloud of electrons. In reality, because they have electrical charges, at the very least, there's going to be some interaction. There's going to be some attraction or repulsion between those gas particles. Right? You see how that's the reality? But we're neglecting that. We're saying we're not going to worry about that. That they're moving fast enough, they're going to go past each other. That effect won't really be felt, not very much. And the last part here is that the temperature of this gas is a measure of its average kinetic energy. Or that's that line over the kinetic energy, the mean kinetic energy. Another way of saying, okay, part 5 of kinetic theory is that it's proportional, which means that it's equal to some constant E times the temperature that the mean kinetic energy is. It ends up that we can figure out what this constant is. It's 3/2 R. Where R is going to have to be the 8.3145 value joule per Kelvin mole. And this constant here, it actually depends upon what kind of gas it is. Monatomic, diatomic, or so on. This is really for monatomic, but we'll just look at simple gases like that. We're not worried about them. Anything we'll talk about. All right. So what we can do now is we have two expressions for the same thing, for the mean kinetic energy. We can set them equal to each other. The mass here we're going to want to use is the molar mass and in kilograms per mole, because we need the units to work out correctly. So I'll write it like that, just like you wrote this.
Is this supposed to be 2m kg?
Where?
The denominator? Yeah, where you have the V2 equals.
This 2 and this 2 cancel.
Oh, okay.
So no. But thanks. But good, that means you're following out. Good. But you see where I just multiplied both sides by 2?
Yeah.
This quantity right here, which is one of my goals here, it's the square root of the mean of the square of the velocities. It's called the root mean square speed. It's simple as this. So we squared it, found the mean, and took the square root back out. And this gives us an expression for the root mean square speed for a gas. All we have to know is what gas it is so that we know its molar mass and what temperature it's at. That's it. That's that right there, okay? That simple little equation, it's really, it's kind of incredible if you think about it, because it relates a macroscopic property, something that you can measure in the lab with a thermometer. You can stick a thermometer into a gas and measure its temperature, to a microscopic property. How fast are those little gas atoms moving about, right? It connects the two worlds, right? The microscopic and the macroscopic. So let's do one for hydrogen. So I'm plugging into that equation there for the root mean square speed, specifically for hydrogen gas at 20 Celsius, right, about room temperature. 3. R, remember, is 8.3145 joules per Kelvin mole. Temperature has to be in Kelvin because of the Kelvin here. So I just added 273.15 to that. There. And this, I already showed you this before. This is the molar mass in kilograms per mole for hydrogen gas. And we get units are going to be like this. The Kelvin cancels. That's how they work. Kelvins cancel. The moles cancel. And we get, as far as the units go, basically the square root of joules over kilograms. And remembering that joules is kilograms meters squared per second squared. Okay. Kilograms cancel. Yes, square root of meters squared over second squared, which is meters per second. Remember when the first calculation I did for hydrogen today, where we calculated the kinetic energy, and I looked up the speed. That was the root mean square speed. It was 1900, right, in that table. So we get something really close to that. We can use this idea that the speed, the root mean square speed, depends upon the temperature and the molar mass, to separate gases based on their mass. It's going to be a mixture, so that means that they're going to be at the same temperature, right? To do that, we have to talk about diffusion. Diffusion works pretty much like this. Well, first of all, let's talk about diffusion. You guys probably know what diffusion is, right? If I were to open up a bottle of perfume or something way back in the corner of that room, eventually I should be able to smell it up here, right? Why? Right? Well, when I smell something, what's happening? Well, that means a molecule of the perfume is docking in a site in my nose, right? And it sends a stimulus to my brain, and I smell, right? So what happens is a molecule has to get from there over here, right? And the process that happens is diffusion. So if you think at the molecular level, what those molecules are doing. Okay, first of all, you open up that bottle. Diffusion. And it's a liquid, right? We'll talk about vaporization in chapter 15, I think. But what happens is some of the molecules of the liquid escape from the surface and they go off into the gas phase. They vaporize. When they do, okay, now it's a gas, and so the things that we're talking about, this picture, the kinetic molecular theory of gases applies to that molecule of perfume. And the thing is, though, it's not in a vacuum, right, or we wouldn't be here, right? There's air in the room. So there's a lot of molecules of nitrogen, oxygen, carbon dioxide, all that good stuff in the room. So this molecule of perfume, when it comes out, it's going to be moving in a straight line, in a random direction, right, until it hits something. Well, pretty soon, it's going to hit a molecule of air. Then it's going to bounce off. Here. And when it hits, maybe it goes back this way, right? Then it's going to hit another molecule there. Maybe go back here. See what I'm trying to describe? Then over here maybe, and then back here, and then here. Eventually, though, it's going to get over here. At least some of them will, right? I know that because I smell it. Made it over here. In a little bit, we're going to talk about how to figure out the distance between collisions, the mean-free path, how often the collisional frequency, these particles collide, and a couple of other properties. But now, diffusion. Effusion is a little bit more constrained. The idea is you have a closed container, and there's a divider in this container. And there's a little hole, at least one, maybe more, right? Put a few. On one side of this container, we have the gas. We're going to start out with just one gas. Not hydrogen, nitrogen, something like that. Or, and it's at some temperature. So the picture is the same. Particles are moving in straight lines, right? Until they hit something, they bounce off the walls or each other, right? Random directions. Negligible interactions, large distance between them compared to their size, all that. Well, if the size of these holes is pretty close to the size of the molecules, the molecular diameter, then pretty soon a particle is going to hit just right orientation. It's going to go through. When it does, it's going to be over here. First particle makes it to the other side. It's all by itself. It's doing the stuff that gas particles do. It's moving in straight lines until it hits something, all that. It's going to bounce around, and maybe it's going to hit a hole and come back, but more likely, because there are more particles here than there are over here, another particle is going to come over first, right? That's good. And this process keeps happening, right? And maybe one of these is going to go back the other way, but on average, more are going to go from left to right than are going to go from right to left because there are more over here. Until you get to the point where the number is the same on both sides. But then the chance of one going this way is the same as it going that way. So then the rate this way is equal to the rate this way, and the number on each side, on average, stays the same. That's at equilibrium. Let's think about how fast that equilibrium is going to reach. In other words, what's the rate of diffusion? Well, what can it depend on? What would change the rate of diffusion? What would make that gas reach equilibrium faster? The speed, right? Right? Because the faster those particles are moving, the more often they're going to get a chance to hit the hole, right? Right? And so the way we say the speed is the root mean square speed. So what we can say is the rate is proportional to the square speed. And we know what root mean square speed is. You guys okay with the 1/2 power same as the square root? Yeah. No? Yes? Yes. So now what we can say is that the rate of diffusion is proportional to the square root of PRT over the mole mass. In other words, at a fixed temperature, now we're going to compare two different gases, right? If they're at the same temperature, which one's going to diffuse faster, the heavier one or the lighter one? The lighter one, right? Because smaller molar mass, it's in the denominator, this number's going to be bigger, the rate's going to be greater. The rate is, say, how many per second, let's say, or per minute, or per unit time. Right? So now if we compare two gases, what color can you guys see best, blue, red, or green? Green. Green? That's none of them, right?
He's lying.
Good red.
Red. Yeah,
Red.
definitely.
Well, if you can't see red, then it's not there. So we're starting out with a mixture, right? Going to let them diffuse because it's it's in the same container. They have to be at the same temperature, right? There's no way for them not to be. What we can say is that if, I don't know, one of these is gas A and the other is gas B, right? Just so that we can keep track of them over here. We know that the rate of A is proportional to 3RT over the mole mass of A. And for B, it's 3RT more mass B. All I've done is I've plugged in from up there. You guys following that? Okay. Another way of writing this. Like that, they're both to the 1/2 power, so we can put them together to the 1/2 power. Is that okay?
I do the same as I can do it.
And then what I want to do now is I want to cancel out anything that's the same. The temperature is the same, you know, because they're in the same container. Temperature cancels, 3R cancels, right? And all this is really simple. Wait. This says that the rate of effusion of gas A divided by the rate of diffusion of gas B is equal to the square root of the molar mass of B over the molar mass of A. It's called Graham's law of diffusion. I'll write it over here.
How did the A and B switch?
Well, okay. So this is 3RT over A, molar mass of A, 3RT over molar mass of B, right? So this by itself, the molar mass of A is on the bottom,
Oh,
and this, the molar mass of B is on the top, you see.
yeah.
So what this tells us is that if we want to, that one way to separate two gases that have different masses would be set up in a fusion chamber, and the one that's going to, well, the lightest one will effuse fastest, right? Because the rate is greater. And so what we do is you set them up, let them effuse, then take this chamber over here. There's still going to be a mixture, but there's going to be more of the lighter gas than there is of the heavier gas. You guys buy that? And then effuse again. Set up another chamber out here. Some holes in this. Let them effuse. There's going to be an even greater percentage of the lighter gas in this chamber. And then keep doing that until you reach the purity that you want. They've done this to separate isotopes. So isotopes, there's not much difference in mass. There's 1 or 2 neutrons different, right? But they can still do it. Let's do an example. Oh, one thing with these problems is sometimes they talk about the time it takes something to effuse versus the rate of effusion. So a rate is how many, say, per second. Right? So if it has a greater rate, is the time that it takes, so comparing rate of A to rate of B, rate of A is greater. Is the time that it takes A to effuse going to be greater or less than B? Less, right? Because a greater rate means it's effusing faster. It's going to take less time for the same amount to effuse. Just make sure you keep that straight in your mind, because sometimes in the homework, you have to be careful. Are they telling you about the time that it takes to effuse or the rate of effusion? Because they're inverse, right? You guys get that? Just to be sure. you're talking about times, relative times, then because it's inverse, it flips upside down. You guys buy this? No? I see some puzzled looks. No, you don't like that?
Is it just because T's on the numerator on each region?
No, which T? That's temperature. That's temperature. Okay, let me back up a second. Identify that. The rate is equal to 1 over the time, or proportional to, either way. Right? Because you guys already told me if it's a faster rate, then it's going to be a shorter time, vice versa. Is that right? And so, the rate of A over the rate of B is pi d over time A. Right? But we also know the rate of A over the rate of B is equal to more mass of B over more mass of A, 1/2 time. That's that one over there. You guys right now?
Yep.
So you have an fusion chamber set up. Helium's one of the gases, and an unknown gas, it's a noble gas, right? But you don't know which one it is in there. So it's the red and the black dots, right? And it ends up that helium escaped from the fusion chamber 5.73 times as fast as this unknown gas. Which gas is it? So what do you think? How are you going to figure that out?
Plug it into the second one. 5.73 over 1.
So is this a rate or an escape time? Is it a time or a rate?
Time.
Rate. It's a rate.
Is it?
Its rate is going to be 5.73 times as fast as the other one. It's a relative rate is what it is, right? What this is saying is that the rate of helium over the rate of X is equal to 5.73. You see that's what that's saying? So it's a relative rate. So we're here, right? This is helium on top, this is the unknown on the bottom. So now we can set this up. Which one goes on the top over here? It's the molar masses, right? So heliums or the unknowns? Unknowns. that means the molar mass of helium, which is 4.00 what? Thanks. It doesn't have to be in kilograms per mole here because it's going to cancel, right? The units will work out. You can just leave it as grams per mole. Pretty simple equation, right? 5.73 equals the square root of that. Solve for this, right? Once we get the molar mass, we can look at the periodic table and see which noble gas, because I said it's a noble gas, right? Let's see which one it is. So we're going to square both sides, solve for the end of it. Is that what you guys get? Yes. So, what noble gas has a molar mass of 531? Xenon. Yeah, pretty close, right? The answer is xenon. You can see how that's really easy to write a multiple choice test question for that, right? Next, mean free path. So remember that perfume molecule coming from the corner of the room over here? What we're going to do now is develop an equation that describes the mean free path for that molecule. That is the average distance that it travels before it hits another molecule of gas. Although we're going to only talk about a gas, a pure gas, not a mixture like the air or the perfume molecules. It'll get you the general idea. So we use L. But again, the picture is this. If we look at a particle of gas, it's going to move in a straight line until it hits something. When it does, another particle of gas is going to bounce off until it hits another one, and so on. And what we're looking at, what we're going to calculate or get an expression for, is the average distance between collisions, the mean free path. And so, if we think about it, the more dense that gas is, the more gas particles there are per volume, the shorter the mean free path, right? That makes sense? If it's denser, it's more likely to run into another particle, sooner. So we can say that the mean free path is proportional to 1 over the number density. You guys buy that? Does that make sense? No? You don't like it? You don't buy it? So if it's more dense, right, that means, N over V is the number density, right? So if the density is greater, bigger number, that means the mean free path is going to be smaller. If the density is less, the mean free path will be longer. That's all that's saying. It's a proportionality, it's not equals, right? So you guys buy that? Okay with that?
It's more or less what?
What's that?
If it's more or less condensed.
If it's more dense, that means this number right here is bigger. which means the mean free path would be smaller. More dense the gas is, the shorter the distance is before, on average, before it hits another gas particle. Do you agree? Good. The rest of you guys okay with that? Okay. Another thing that we can say is that the surface area of that molecule, the bigger it is, the greater the chance that that particle of gas has of hitting another particle of gas, right? The bigger it is, the shorter its mean free path is going to be. If we treat it as basically a sphere, you can write the surface area as pi times the pi r squared, which is the diameter over 2 squared. So we can say the mean free path is also proportional to 1 over the molecular diameter squared. You guys buy that one? No, Travis?
What happened to pi?
It's in here somewhere. Where'd it go? All I'm doing is setting up proportionalities, right? And what I'm going to do is I'm going to wave the magic wand and tell you what the proportionality constant is in just a second. Okay. But you see, because the proportion, any constants, we don't have to write when we do proportionalities, right? Because that's going to be sucked up into the constant of proportionality. You guys all right with that?
Is that 2 or Z? The bottom of D.
2. This is, because the radius is the diameter over 2, right? All right, so combining these two, you get that. Now the magic wand, it ends up that the constant of proportionality is pi times the square root of 2, square root of 2 pi. One over that, excuse me. All of this is to get an expression for the mean free path in terms of things that we can measure. Let's see. The number of gas particles. We could write it as the number of moles of gas particles times Avogadro's number, right? You guys buy that? You've done this plenty of times, right? Let's see. But from the ideal gas law, see the N over V here? We could just write that as P over RT. You guys follow that? Plugging in. if N over V is P over RT, then RT comes up on top. It ends up that we can look up, people have measured molecular diameters, so we can look that up. It's just Avogadro's number. We can measure the pressure, we can measure the temperature, right? That means we can look up the molecular diameter, measure the temperature and pressure, and that'll give us the mean free path. No?
It's just a lot.
That's a lot. To keep everything in perspective, Alexander, this is the derivation. I'm showing you, where it comes from. As a practical matter, what you're going to do is use that. Okay.
What's R?
Is that R? Okay, let's talk about units, right? It's a gas constant, right? Because it came from the ideal gas law.
Yeah, I just meant which one.
Good question, right? We're going to need things here. Okay, we're going to want like meters here. We want SI units. That means we're going to use joules per Kelvin molecule, pascals per meter cubed. T is going to be in Kelvin, of course. And pascals for the pressure. The book has a list of some molecular diameters in picometers. Hydrogen is 270. So we measure the pressure, measure the temperature, look up the molecular diameter to get the mean free path, just plugging in. One times 10 to the 5th pascals per bar. You plug all those numbers in, so R, T, pressure in pascals, Avogadro's number per mole. The molecular diameter in meters, right, picos 10 to the minus 12. And then square root of 2 pi. You get 138.7. Speed meters. I better get, that's wrong. Let me calculate it.
That's what you got. Oh, 1 second.
So we get 1.31 times 10 to the minus 7 meters. Do you guys get the same number? No?
No, 1.29 times 10 to the negative 7.
Okay. Yeah, pretty close there. Anybody else get?
Oh, I said I got 1.37.
1.37?
I got that.
Okay.
1.31.
I might have done it wrong, let me try again.
No.
I believe 1.37 because that's what I have in my notes.
I got 1.31.
Okay. Take the mean of all these numbers, right? Distribution.
Did you get something like this? Am I really-
Yeah, no, that's right.
Oh, it's up there.
Yeah.
You're just double checking?
Yeah, I was just making
I
sure.
got 1.31.
I got 1.31 too.
There you go.
That looks right.
Yeah.
Yeah, I got half 1.31.
I got 1.31 too.
Anyways, that's the mean free path. It's not very far, right? But if you look at that, what we can do is we can compare that to the molecular dimension, right? He's still not getting the number?
He erased it up.
So 70.
We take the ratio of the mean free path to the molecular diameter. That gives us one of the parts of the kinetic molecular theory. Remember, one of the parts of the kinetic molecular theory said that the size of these particles is really small compared to the distance between them. What that means is if we take the mean free path divided by the molecular diameter, it should be a pretty big number. That make sense? So we take L over D. 270 meters. You can see already it's going to be a pretty big number, right? Like 3 orders of magnitude. 485. So what that shows us is that for hydrogen at 0.958 bars and 22 Celsius, that the distance between particles on average is about almost 500 times that, the size of the particle. So yeah, the kinetic molecular theory is holding up because it said that should be true. Another thing that we can do is we can talk about the collisional frequency. When I say that we can do, it means you're probably going to have to do it for me.
Yeah, he was just deriving it. Yeah.
I can't even handle units.
We use Z.
We'll have to do that every time. Yeah. Just once in a while. Good old hunting.
So what it means is the number of collisions per second per unit time. We can think about that. As the distance it travels per second divided by the distance per collision. Distance cancels, we get collision per second. You guys see how the units work out? We know how to get both of these things, right? This is the root mean square speed, how far it travels per second. This is the mean free path, right? Distance per collision. Does that make sense? You know, the distance per second, you know, the root mean square speed divided by the distance per collision will be how many collisions per second, right? The collisional frequency. So root mean square speed over the mean free path. So for hydrogen, let's see. Yeah, we already did the root mean square speed, didn't we? Yeah. Right. That was at 20 Celsius. It was like 1,900 or so meters per second, right? Get about 1.5 times 10 to the 10th per second, something like that. So that's a lot, right? Yeah, that's. So now you know how to calculate the collisional frequency. Compare the mean free path to the molecular diameter. Mean free path, mean square speed.
Within 1900.
What's that?
Within 1900.
We calculated this like at the beginning of class today. It was, you know, it was at 20 Celsius. Close enough. The last thing I need to talk about in this chapter is how to take into account non-ideal behavior of gases. What's called the Van der Waals equation. So everything up to this point, we've assumed that a gas has been an ideal gas. When we say that, what we mean is that it basically follows the concepts in the kinetic molecular theory of gases. That is that straight line motion, right, until it hits something, random directions. The distance between the particles is large compared to their size. And importantly, that there are no interactions between the particles. And that this also that we've assumed that the size, okay, this is the second one, that the size of the particles is negligible. That's what we mean when we say the distance between the particles is large compared to their size. So in the picture of an ideal gas, we're basically neglecting, in that volume of the gas, in that balloon of helium, the actual size of the helium particles. You guys see that? That's one of the things that we're neglecting, we're not taking into account. We're also neglecting any of these interactions between them. And so if we think about what effect that would have on a real gas compared to an ideal gas, the volume, okay, we're looking at the ideal gas law, PV equals nRT, and we're going to modify it a little bit to take into account that gases are real, that they actually have some volume, that they actually do interact. So let's look at the volume first. So if the volume of an ideal gas, that's the volume that it would have without taking into account the actual size of the gas particles. Would the volume of a real gas then, which does take that into account, do you think be larger or smaller?
Larger.
Larger, right? Because you have the volume that's occupied, which is the ideal volume, plus the volume of the gas particles. You guys buy that?
Yeah, you say the real gas will have a larger size than the ideal gas. Because you're taking into account. Yeah.
Plus something, right? And what we can say about that is that the more particles there are, the more volume they're going to take up, right? And so if we use N as the number of moles of gas times some constant B, we write it like this. This constant is going to depend upon which gas it is, right? We can look these up. So I'm going to rearrange this, say V ideal equals the volume of the real gas minus this constant. Come back to that in a second. Now let's look at the pressure. Because the thing that affects the pressure is going to be the interactions between the particles. The interactions between the particles are going to be mostly attractive, which means that in our picture of the gas, as these particles of gas are zooming past each other, when they get close to each other, if there is, and there is this real attraction, it's going to slow them down a little bit, right? Because they're attracted to each other as they go past them, they're going to keep on going, right? Which means that when that particle, after it's gone past another gas particle and been slowed down, when it hits the wall of that container, it's going to be moving a little bit slower. It's going to exert a little bit smaller force over that area, which means the pressure that it exerts is going to be a little bit lower. You guys follow that? And so overall, this is happening to all the particles in this helium balloon or whatever it is. So the pressure that it exerts, the real gas is going to be less than the pressure that we calculate for an ideal gas where we don't take that attraction into account. You guys buy that? Now, what that's going to depend upon is it ends up the density, right? The greater the density of the gas, the more likely it is to run into another particle and have that attraction occur. You guys buy that? Sort of the same argument we used with the mean free path. So we can say this. The ideal pressure minus some constant, called A, times the density. The density is just say the mole density is just the moles per volume, right? Squared. And we're going to square it because it's the same idea as with the diameter, right? So we're again, A is a constant. That also depends upon which gas it is. And you can look these up. These are called van der Waals constants, by the way. We'll get to them. The ideal gas law, PV equals nRT, or it's the ideal pressure and the ideal volume. We take these two expressions and we plug them in. We get what's called the van der Waals equation. Where this is the first step in attempts to correct for the real nature of gases. The only thing one of the things about the van der Waals equation is that you have to know what these constants, A and B are, and there are tables of them. Table 13.5 on page 458 has some of them for some of the gases. You don't have to memorize it or anything like that. I'll give you these if you need to know. But you do need to know the equation. The thing about this is that it ends up that it's cubic. It's a cubic equation in V and N, in volume and number of moles. I'm not going to ask you to solve a cubic equation because either you know how to make your calculator do it and it's real easy, or you don't and you have to do it by hand and it's really tedious, right? So basically, I'm not going to ask you to solve the van der Waals for volume and number of moles, but I will ask you for either pressure or temperature. And then it's linear, so it's not a problem. I'll give you the van der Waals constants. So, it's basically the idea is, I think a homework problem has you calculate, I think the pressure of a gas using the ideal gas law, and then van der Waals equation, and comparing the two and seeing how they're different from each other. How the real pressure is different than the ideal pressure. There are hundreds, I think, of other equations that do the same thing, that are more complicated. This is just the idea of how you kind of take that stuff into account. So that's chapter 13 for this. Start on chapter 14 on Wednesday, which is thermochemistry.